welcome to our regular GOAT seminar. And today it is my pleasure to welcome Jakub Mareček, my longtime friend in our seminar. So Jakub in the past was a member of several institutions, Masaryk University in Brno, University Nottingham, University of Edinburgh and IBM Research, and currently he's a member of Czech Technical University, and he will give us a talk with the title on the ergodic control of ensembles. So if you have any question, please write it to the meeting chat, and I will try to somehow relay these questions to the speaker. So that's it.
Cool. Thanks so much. So it's a great pleasure and honor to be speaking in a game theory seminar in particular. I should like to say that this somehow tries to bridge control theory and maybe stochastic analysis and maybe some of game theory, but my background is not game theory per se. So I should like to explain in as clear terms as I can what we're doing, and I'm maybe happy to sort of discuss the relationship to game theory towards the end. So what I'll start is hopefully relatively simple, and it could be seen as congestion game, maybe repeated and maybe stochastic variant of a congestion game, but a congestion game. And then I'll get to the main result, which somehow is a broad generalization thereof. And then we ask the sort of a question of how to evaluate the quality of what we are doing in practice. And that's somehow a question in the margin for the theory, but which is very important for the practical deployment of such things. And so we have done some work towards that. And also, before I start, I should like to say that this is based on the joint work with a great many fabulous colleagues, and those have only partially overlapped throughout the 3 parts. So I'll try to always add the acknowledgements as necessary, and most of them have at least at some point been with IBM or visited IBM, and throughout most of those papers there would be Bob Shorten as a co-author, who was at IBM and now is at Imperial, and then other people joined in and then left somehow the team. So for the beginning, let's start with something which is very concrete. So let's have a roads authority. A roads authority has a number of sensors deployed throughout the road network, and it aims to provide some information to the road users, which can be seen as the agents 1 to n, such that when they observe the aggregate behavior of those road users, that means the total number of cars passing a certain place on a certain road, they get some behavior in terms of these aggregates that is stable, right? So our first concern is not necessarily the well-being of the individual agents, but the social objective of nice behavior in terms of the aggregate utilization of the space-time of the road network, right? So if you're familiar with the concept of congestion games, here these sort of costs would be the costs of the congestion game, and if you have a certain number of road users, here you would compute the delay involved in the congestion game. and then this would give you the overall sort of a, right? So this is just a control theoretic symbol to denote the delay in like processing between the realization and you sending out the new signal. Pi would be the signal. Here, this sort of omega would be a certain type of an agent. So this is actually quite a common format, and in transport engineering, people usually consider degree 4 polynomial cost functions, or the functions involved in such a setup, and have been studying similar approaches for a long time. And for perhaps the simplest example, you could consider two road links, one which could be, for instance, local road, and the local road would have sort of increasing travel time as you increase the number of occupants, maybe quite steeply, and then you would have something like a freeway, a highway. And on the highway, for a long time, you can add the occupants without increasing the travel time until it starts sort of have an impact on the travel time, right? And now you would like to split the road users across the two road links, the local road and the highway. And it turns out that although sort of on the local road, you have some sort of a higher number for the travel time at the beginning, and at the end, it is still socially optimal to send roughly 1/5 of the users along the local road and only the rest on the highway or freeway, right? So this is one particular example. And so your sort of goal as the road authority may be to achieve this social optimum such that you minimize the total travel time across all of the road users. And you would like to achieve that social optimum as a sort of a provider of something which is truthful, of signals which somehow are very closely based on the history of your observations of the true travel times, right? But at the same time, it's clear that if you are the transport authority and you always broadcast the scalar for the most recent travel time, so for the two road links, you would have the travel time based on the number of agents in the previous period and the number of agents on the other road link in the previous period. And the agents pick the road link which somehow minimizes the travel time, then you would have a very poor sort of behavior overall. And that poor behavior will be essentially alternating congestion. So first you announce that this sort of a road link takes 5 minutes, that road link takes 6 minutes. All of the agents like to take the 5-minute road, and then this will turn out to be maybe 10-minute road in practice, whereas this sort of a road which was originally suggested to be 6-minute road may turn out to be, I don't know, 4-minute road, right? So these sort of these things can lead to some nasty behaviors. And maybe the simplest which we can do here is to provide intervals, right? So instead of providing the agents with a single value, we provide them with an interval which is based on the minimum and the maximum of the observed values. So if the travel times on the highway were in the past 5 periods maybe 5, 6, 7, 8, 9. We can give the road users the information that the travel time is between 5 and 9. And then the agents need to somehow trade off the risk of this being a 9 travel time with the possibility that this will be a travel time of 5 road link. And at that point, because this sort of perception of the risk or the risk aversion varies across the users, you're able to somehow split up the agents across the road links. And if you know reasonably well, or if you can estimate the appetite for risk, you can then get closer to the optimum. And so sort of the first result is not really talking about optimality. It only talks about the weak convergence of the congestion profile in the sense of the numbers of road users or in the sense of the travel times. And we're saying that under some very basic assumptions on the distribution of the risk aversion, sort of the convexifying coefficient in the way the users perceive the interval, you have this weak convergence. Now, this is obviously very contrived sort of assumption. And it essentially says that in each period you sample a new population from some distribution of populations. But we are showing more elaborate things for more elaborate population profiles or sort of ways of evolution of the population, and for more elaborate ways of working with the signal. So whereas here we were saying for the 5, 6, 7, 8, 9, we maybe provide an interval based on the minima and maxima. We can also provide something which looks like a variant of the mean and standard deviation or such like. And this is sometimes known as exponential smoothing. And and then we have all kinds of more complicated models of the population dynamics. So for instance, we can represent the population with some Markov chain, where essentially the state corresponds to this convexifying coefficient, and the probability of the transition between state and state is given by the distance between those two states. Right, so we have like some complicated definitions, but this is a very broad sort of outline. So for instance, if you want to capture some time varying aspects where there is a different sort of a risk profile in the morning and different in the noon lunchtime and different one in the evening, you can sort of clearly represent that by some small Markov chain like this. If you want to introduce some uncertainty, it's easy to do. You just increase the state space. And so sort of here we're showing that if you have some nice properties of the cost functions, which are somehow related to the properties of the Markov chain, then you again get the same behavior. You get some weak convergence to the congestion profile. Now you can construct all kinds of more difficult sort of assumptions and again get the same behavior. So this was sort of a short introduction to what we are doing, right? So sort of there is this concept of a discrete time repeated behavior of the agents in response to some signal, where in these cases the signal is prescribed by the central authority using some relatively basic policies, relatively basic rules. Now, we obviously wanted to do better, and we wanted to make a more general statement about what would be the constraints on what the central authority can do, such that we still have this nice behavior, this convergence to unique invariant measure, or to some sort of a distribution in terms of the congestion profiles. And that's indeed what we would like to sort of explain in the rest of the talk. And so you can generalize the picture you have had so far, where there was a central authority providing some information about the travel times to the individual drivers, and then some aggregation of the behavior of the drivers. So this driver picks route A, this driver picks route B or route B, and then we aggregate this, and we know that on route B we have one driver, on route A we have one driver with some delay and corrupted by some filter, maybe introducing some noise, measurement noise and such like. We compare what we would like with, which is called a reference signal, with what we actually get, and the error, the difference between the two, is passed again to the controller, right? And so sort of in this setup, we would like to come up with a characterization of the filters and controllers which allow for some reasonable behavior of the closed loop. And in the process, we introduce a new sort of a notion of what is a reasonable behavior. So first, it's clear that we would like the controller and the filter to guarantee that all times we are within some resource utilization limits. So for instance, if you know how many cars can fit on a road, you don't want to have more than a certain number of cars going in that direction. But there is also a more involved notion, which is predictability, right? So you would like to have some notion of fairness across all of the agents, such that independent of the initial condition, their route choice is somehow the same as for someone who would have started from the same initial condition, or independent of the initial condition, right? So this notion of a predictability can be thought of as sort of an individual's perspective, as a central authority's perspective on such a congestion game or resource allocation game, right? And so in two sentences, our results essentially show that most control theoretic approaches to this problem, which feature integral action, destroy the ergodic properties, even in the most simple cases, in the sense that they cannot guarantee, and in practice do violate, this predictability. And on the other hand, we show novel control policies, novel approaches, which guarantee that for a broad class of stable controllers and filters, we can obtain this ergodic behavior in the sense of both guaranteeing feasibility and predictability. So first, for the negative results. So if you have never seen control, this may seem somewhat obscure, but in like control theory 101, sort of even in ČTU there is Katedra řízení and such, people would study the PI controller and the PI controller would have some integral action where you're looking at what has happened in the past. And then there are all kinds of derivatives such as the PID controller, and but we reason anything which has this integral action, which has some sort of a spectral representation. And here we have some simple example with 10 agents and some sigmoidal activation of those agents. We have some PI controller and we have some lac approximant of the PI controller. So it's relatively clear that when we have the 10 agents, we would like to regulate the resource use to 5. So for instance, 5 of the agents pick route A, 5 of the agents pick route B. We get something which is not perfect. So for a single run of the simulation, you get something which varies around the value 5 for the aggregate utilization of one of the route links. And that's the case for many controllers. So PI controller, the sort of a control theory 101, would guarantee this sort of a behavior in terms of the aggregate utilization, and the same for the lac approximant. But what we are showing in the next picture would come as a control, because here we are showing that essentially depending on the initial allocation, the behavior for a single agent, so this would be agent whose initial value at time 0 was 50. This would be an agent whose initial value at time 0 was minus 50. The behavior is sort of a fully determined, or up to the stochastic aspects, fully determined by the initial state, right? So this notion of predictability for the individual, where you would like to have this long run the same for everyone, is violated, right? Whereas in some other controllers, such as this lac approximant, you get the behavior somehow being nice and sort of a convergence to the same value. So this can be seen for all of the agents essentially. So with the PI controller, if this is the sort of initial condition of the agent, and that could be any of those agents, and this could be the average allocation after 1000 steps, you get this sort of a threshold where if the initial state is too low, they stay with that low state forever. If the initial state is somehow higher, they receive some high average allocation forever. And that's not the case for the lac controller, right? And that's in some ways sort of a clearly the result of the control signal, the information provided, being different. So in the PI, we generate a different control signal, and then in the response, the agents behave that way, whereas with the lac controller, or sort of a more suitable policies, we do get the right information, and when you have the right information, the agents respond correspondingly. Right? So here, this was just a proof by example that sort of in one case this happens. But we have a theorem which is somewhat complicated in its wording, but essentially it says that if you have like a very standard moving average filter and any controller where you can guarantee that the set of the output values of the filter is finite, then you can't have the unique ergodicity. And so in particular, if the actions of the agents take some sort of values from rational numbers, then you have this sort of destruction of the ergodicity for anything which involves the integral action. So for instance, the PI controller, but also many other controllers, switched controllers, and such like, as we show in the papers. So technically, this uses something which I'm quite proud of personally, and it's a coupling theorem by Hairer. So Hairer won a Fields Medal maybe 6 years ago or such for his work on stochastic differential equations, mostly in physics. But one of the very important contributions of his is sort of a two-way result on couplings. So couplings are, in some sense, the quite complicated subjects in terms of definitions. So you first have to have some state space, then some measure space over that state space, then some path space over which is sort of like a infinite sequence of values from the measure space over the state space, and then you have a product space over the two path spaces, and then you have a measure space over those products of the two paths. But in principle, you're saying two things couple if with probability 1, they eventually reach the same trajectory in terms of the states. Right, and this is a well-known sort of a notion. There are whole textbooks from 30, 40 years ago on the coupling method. But what Hairer has done is the following. So he has shown that if you have two ergodic invariant measures, then the following are equivalent. So the two ergodic invariant measures are the same, which means that you have a unique ergodic invariant measure, and there is an asymptotic coupling of the two. Right? So people knew that if there was an asymptotic coupling, you would have a unique invariant measure, but people didn't know that sort of the other way works as well. And so we particularly use this to show that you have this sort of a violation of the unique ergodicity. So now we have lots of positive results with various assumptions on the systems and filters. And so for the initial part, we assume that there is a linear controller and a linear filter with arbitrary matrices. And then we show that when you have the evolution governed by the linear stochastic difference equation like this, then for every linear stable linear controller C and stable linear filter F, the feedback loop converges in distribution to unique invariant measure for a particular setup in terms of these probability functions. And if you have some sort of a nonlinear system, we can do a similar result. The notation gets ugly, but the point is that we have some nonlinear maps called FM, which map from some extended state space, which are the state space of the agents, the filters, and the controllers, again to this sort of extended state space. And then we have some notion of indexing over those maps. And then we have some Lipschitz constants for each of those maps. And essentially here we're saying that if these maps are contractions on average, then with respect to the measure you sort of sample with, then the system can be uniquely ergodic. And finally, we have some positive results when the agent's actions are limited to a finite set. So you have no continuity of those maps, right? So you have, for instance, each agent taking roads 1, 2, 3, and not being able to vary continuously between roads A and B and C. And then you have some graph, and again, you can sort of reason about the properties of that graph such that you get this unique invariant measure. And so that's what we would have for the positive results. And all the details are in two papers, the second of which has appeared last year. So this in some ways, I think, is a useful way of assuring both the aggregate behavior and the individual perspectives behavior of such closed loops. And I think that maybe the transport application at the beginning doesn't quite do justice to the breadth of the possible applications of this. So for instance, if you have some smart grid applications, such as what people call demand response management, they would envision that people have, for instance, electric vehicles being charged, but that they allow for some flexibility in charging them. So the distribution system operator can decide remotely, independently, as to whether to charge the vehicle at a given point in time or not. And so in this setup, you would, like, from the perspective of the distribution system operator, to assure that the total closed loop system is stable, right? And that's precisely the motivation of the distribution system operator, to maintain the voltage stability. But from the point of view of the customer, you would also like to have this predictability or fairness. You would like to know that your vehicle gets charged independent of the initial condition about as much as your neighbor's electric vehicle. And while that may seem greedy and selfish, there could be like very similar applications across this smart grid, which are actually like public health important. So for instance, most supermarkets now have similar systems fitted in, which control the freezers. So the supermarket would have a massive freezer storage, and in that storage, they sort of run the system so as to allow for some flexibility on the distribution systems operator, sort of balancing the grid. And when they do so, they can defrost the whole freezer if this does not sort of have this predictability property. And so if you're Lidl or Tesco and you allow for this demand response management, you allow for this variation in the power that you use for the freezers, you would like to make sure that it doesn't happen that one of your freezers gets defrosted while the others are left frozen. And that's the same story, right? So sort of you care not only about the aggregate performance, about the total power utilized across all of the freezers, but you also care about the amount of power utilized by the individual freezers. So that's for the first two parts. And we have recently been extending this in various settings. So Raman, who is a student in Dublin, working with Bob Shorten, and others with essentially has focused on first extending this to the setting where the population has even more widely varying behavior, for instance, changing some time instance by a substantial amount, some sort of a jump. And what would happen to the stability, because you have to redefine what stability means when you have such jumps. And then we have tried using this in social sensing, and we have used similar techniques in two-sided markets. So that's a draft which will be out shortly, hopefully. And towards the end, I'd like to mention an interesting challenge, which I think is by far not closed. And that's somehow this counterfactual reasoning about what would have happened if instead of this system, you had another system, right? And that's very non-trivial, because in some ways, that's the question that people at the transport authorities or power systems authorities always ask before they deploy the system. But you, as a sort of a game theorist or control engineer, don't have a great simple answer, because in some ways it's very hard for you to provide a model of the system prior to the information being provided, and to develop the system which really develop a model of the system which really faithfully models the response to the information. And some time back, maybe 3 or 4 years back, we thought that sort of this needs to sort of reduce to some well-known statistics, and that if we try a bit harder, we will surely manage to sort of resolve all of this in no time at all. But it turned out that in the process, we figured out that even very simple building blocks in terms of robot statistics didn't have great theory behind them as of yet. And so in some ways, the two simplest building blocks we were looking for was parameter estimation in Gaussian mixture models corrupted by noise. And for that, there was no good theory, no good guarantees, and we had done some. And then online learning of linear dynamical systems. And again, there were no good guarantees, and we've done some. And so this is this turned out to be a much more elaborate than we had imagined, and we still very much believe that this is something we should do better. So essentially, in that setup, you have the observations of the closed loop. So you have the observations such as this, and you have the observations such as these. And based on those, you would like to estimate the behavior of the agents and the filter. And as I mentioned, this is not real. With that, I'd like to maybe conclude. So I think that the 3 take-home messages would be that most practical applications I've come up with, or I have sort of studied, involved some closed loops. We produce some information, people respond to the information, we observe their responses, and based on those responses, we produce some new pieces of information or such like. And sometimes these are not like simple closed loops like this, but sort of more like data nodes, where There are many streams of information which come into various parts of the decision-making process. For instance, the users may have information from both Google and the overhead displays on the highway or similar. And when there are those multiple streams, it's quite hard to reason about the closed loop behavior. But still, like the reasoning about the closed loop seems very important and much more important than reasoning about the epsilon in the optimization within the controller, if you can't guarantee that the controller within the closed loop has the behavior you would like to see there. And then finally, then the system identification, the questions of what would be the correct model are non-trivial. So even in the most simple cases of like the two Gaussian mixture model, you get nasty non-convex optimization problems. And while they may not be easy to cast in P and NP because they deal with floating point values or real values, you can find very hard problems in there, such as NP complete over reals or such like. And so definitely that's like one more dimension where there is much more research that could be done. And with that, I'd like to ask for any questions or comments.
So we would like to thank you very much for a nice talk. And yeah, now how to do the questions. So if you have any questions, please ask, or if you don't have a microphone, then you can write it to the chat and I will try to read it to the speaker.
So Tomasz was sort of expecting some questions before we started. So I wanted to mention that actually the first part of the talk is completely practical. So this was motivated by like a real desire of the city of Dublin City Corporation, to broadcast some information to the road users in Dublin. So sort of when they are on the when they're on the ring road around Dublin and want to go to the city center but don't know which of the radial roads to use. And so sort of this actually was based on like very real sort of problem. And the second part with the generalization, as you can tell, this is more trying to push it as far as it goes in terms of the abstraction. And that's also the direction we're now taking with Raman in terms of the follow-up work. So that there we consider various notions of nonlinear controllers and filters. And there are many types of restrictions of the controllers and filters you can consider, such that you still sort of guarantee this unique ergodicity.
Okay, maybe I would have one question. So I wanted to ask whether you considered like how difficult it is to compute the optimal signal for the whether like some computational complexity is involved in some of the considerations or something like that.
Right. So it depends on what you assume you know, right? So so there is this one part like where you want to estimate what is this, what are the S's or what are the omegas, for instance, in the first part. And then the second is when you know this, how can you pick the C? or what you can do in this C. And in the control theory, a natural choice for this C would be something called model predictive control, where you're looking at some of this past. You have this model, which is given by you estimating these and these, and you sort of optimizing over what would have been the best choice given the sort of what you have and your estimate of these systems and filters. And in that case, the complexity depends on whether you consider atomic games, sort of like divisible amounts, or non-atomic games. And in the atomic games, where the resource cannot be divided, you quickly reach sort of quite difficult problems, right? So sort of the non-atomic games usually lead to some integer programming in the controller, and unless the problem is very nice, such that you have some total unimodularity, you run an exponential time for the sort of for the best part. And there are some simpler cases where you have non-atomic games and where this can be solved using a convex programming, and that's maybe a lot easier. So to any fixed precision, you can compute the optimum in polynomial time on the Bloom-Smale ship machine or something. And right, but like our focus was mostly on what would have been a good constraint to add to such an optimization problem, such that you can guarantee that the closed loop has some nice behavior. And that's in some ways independent of the computational complexity of the problem you add this to. So independent of whether this is atomic or non-atomic, in here, which obviously influences what is the computational complexity. We would like to be able to tell you the correct constraints to add here, such that you can guarantee the nice behavior of the closed loop.
Okay, thank you.
All right, so is there one last question or comment? Okay, doesn't seem so. So thank you very much for the second time for discussion. Thank you for attending our seminar.
Cool. Thanks so much. My pleasure.